All right, good morning. So, okay, let's get started. All right, so last time we actually sort of saw an example which had only two variables, and we saw how we can solve it using the simplex method. And hopefully you have some idea of how the method works. So that example was a maximization problem. Now we're going to turn into a minimization problem just to illustrate the difference, basically. So this is example number 2. So suppose that I want to minimize x1 minus 3x2 subject to x1 plus x2 is less or equal to 6 and minus x1 plus 2x2 is less than or equal to 8. So what I'm going to do is, first of all, again, I have only two variables, and since I have two variables I can solve this problem graphically. So first I'm going to try to solve the problem graphically, and then I'm going to solve the same problem using the simplex method, okay, just like we did on Monday. So let's start by drawing the feasible region. So what does the first constraint look like? So this is my x1 axis and this is my x2 axis. So it actually goes through 6 and 6. Okay, so it actually looks like this line right here. So which side is the correct side? So the origin is feasible, so as a result, this is the correct side. So by the way, everyone knows how to do this, right? So, okay. So let me look at the second constraint. So if x1 is 0, x2 is equal to 4, and 4 is somewhere over here. And if x2 is 0, x1 is equal to minus 8. So minus 8 is somewhere over here, basically. And it goes through these 2 points. So this is the line corresponding to minus x1 plus 2x2 equals 8. So which side should I pick again? So again, if you just plug in the origin is feasible. Okay, so as a result, the origin is in the correct side. So I have to pick this side. Then I have non-negatives of x1 and x2. And as a result, my feasible region will be given by this shaded area, basically, okay? So this is what my feasible region looks like. So what's the next step? I need to figure out my ISO cost line here, right? So this is a minimization problem. All right, so let me look at the line that goes through x1, or that's given by the equation x1 minus 3x2 equals 0. So it goes through 0, 0. Okay. So I'm going to need one more point, right? So if x1 is equal to 3, x2 should be equal to 1. So which means that 3 is somewhere over here, and 1 is somewhere over here, basically. So as a result, it actually goes through these two. These two lines, these 2 points, okay? And then my c vector is given by 1 and minus 3, okay? And 1 and minus 3 actually points in this direction. Again, that's perpendicular to my ISO cost line. But this is a minimization problem, right? So the improving direction is the negative of c, basically. So if you negate c, then I should try to push this line as much as I can in this direction. And basically, it's not too hard to see that this will be the optimal solution, okay? Of course, those two blue lines are parallel to one another, okay? At least they should be. Okay, so now I'm going to instead try to solve the same problem using the simplex method, okay? So to apply the simplex method, the first step is to turn the problem into standard form, okay? So the problem is not in standard form right now, but we know how to do that. So basically, the only problem is that my constraints are not equality constraints, right? So I need to turn them into equality constraints. So how am I going to do that? Well, I'm going to add a select variable for the first constraint. We can call it x3. And then I'm going to add a select variable to the second constraint. We can call it x4. So what I'm going to do is I'm going to try to set up the tableau directly. Okay. So remember, we define a new variable z for the objective function. And then I have my variables x1, x2, x3, x4. and I have my right-hand side vector. Okay. Now, what does rho 0 look like? Well, remember, z was the dummy variable that we defined for the objective function. Okay, so z is equal to x1 minus 3x2, 3x2. And if I put everything on the left-hand side, then I have an equation in terms of z, x1, and x2. And what are my coefficients? So the coefficient of z is 1. The coefficient of x1 will be minus 1, right? So be careful about that. So I'm putting everything on the left-hand side. So as a result, I have minus 1. And I have 3, basically. And everything else is zeros, right? So essentially, this is the rho corresponding to the objective function, or rho 0 in other words. And rho 0 is z minus x1 plus 3x2 equals 0. Okay? So remember, essentially what we do is we just set the objective function equal to z, and then we put everything on the left-hand side, and we get this equation. All right, so what about rho 1? What does rho 1 look like? So remember, there is no z elsewhere, so it's going to be 0. So what does rho 1 look like? So I'm going to look at this first constraint. I have x1 plus x2. Now, after changing it into standard form, I add a slack variable that I call x3. So as a result, I have 1 here as well. But there is no x4, and the right-hand side value is 6, basically, okay? All right, so what does rho 2 look like? So again, there's no z. So minus 1, 2. Then I need a second slack variable. There's no x3, but there's x4, and the right-hand side value is equal to 8. All right, so what are my basic variables in this solution? Exactly. So essentially, remember, z is always basic, so we never count it. Okay, z is always part of the basic variables. So we look at our decision variables, and what I'm looking for is the columns of the identity matrix. So this is the second column of the identity matrix, right? And this is the third column of the identity matrix. So since I have the second column here, x3 is the corresponding variable. And since I have the last column here, x4 is the corresponding variable. And z is always a basic variable for the first row, or for row 0, okay? All right, so what are my basic variables here? In the solution? x3 and x4, okay? And what are their values? I have 6 and 8, okay? What are my non-basic variables? x1, x2, and their values are both equal to 0, okay? And what's my objective function value? So I'm going to look at the right-hand side of row 0. Again, I get 0, basically, okay? So let me go back to my picture again. So this is a basic feasible solution, right? So which solution, which corner point does it correspond to? Well, since x1 and x2 are both zeros, essentially, it actually corresponds to this solution right here, okay? So right now we're at the origin. And then we can ask ourselves the same question that we did last time. So is this the best we can do? Okay. Now, unlike the previous example, this is actually a minimization problem. Okay, so my goal is to decrease the value of z. Now, okay, so I'm going to try to decrease the value of z. So smaller z is the better off I am. And right now I have two non-basic variables, which are x1 and x2. And I'm going to ask myself the following question. So should I increase x1? Okay. Well, let's see. So what happens if I increase x1? Well, if I increase x1, I mean, the easiest way to think about this is just look at row 0. You know, z and x1 have opposite signs, okay? So which means that to satisfy that equation, if I increase x1, I have to increase z as well, okay? So which means that increasing x1 does not help me, basically, okay? And indeed, if you look at the picture, so if you want to increase x1, then you actually go to this corner point, but this corner point is actually worse, right? So your objective function actually increases as you go in this direction, okay? On the other hand, z and x2 have the same signs, so which means that if I increase x2, which is currently non-basic and has a value of 0, then z has to decrease, right, so that the equation is satisfied. So as a result, I need to increase x2, which means that x2 is my entering variable, okay, which we denote by this. So first of all, I just realized that, you know, if I increase x2, then my z value will actually get smaller, okay? So the second question that we pose is the following. So how much can I increase x2? So now, essentially, we're at this point, and we want to move in this direction, basically, okay? So we just realized that by moving in this direction, we're going to actually achieve a better objective function value. Better means smaller for a minimization problem. But as you can see from the picture, you cannot increase x2 indefinitely, right? So you cannot increase x2 as much as you want, so you have to do something about that. So what we do is we call the ratio test, basically, right? So that we did last time. So what do? Well, so we look at the columns underneath the entering variable, okay? So we ignore row 0 for now, okay? We look at row 1 and row 2, and we only consider positive entries here, right? So we explained it last time, so we're only interested in the positive values here, okay? And then what I do is, I look at the ratio of right-hand side value to this entry. So for the first one, I'm going to have 6 divided by 1, which is equal to 6. And for the second one, I have 8 divided by 2, which is equal to 4. So what do those ratios mean? Well, basically, the first ratio tells you that you can increase x2 up to 6, and you can still satisfy the first constraint, okay? And the second ratio tells you that you can increase x2 up to 4, and you can still satisfy the second constraint. And indeed, if you look at the picture, this is my first constraint, so I can increase x2 up to 6, and I can still satisfy this constraint. And this is my second constraint. I can increase x2 up to 4 and still satisfy this constraint. If I go beyond 4, then I'm going to violate the second constraint, right? So which means that the second constraint is the binding one, is the more restrictive one, okay? So as a result, this is my... So this is called the ratio test, and since we picked the smallest value, this is called the minimum ratio test, okay? So I'm going to abbreviate this MRT for short. That stands for minimum ratio test. And the minimum ratio test actually determines which variable will leave the basis. Okay, so we decide that x2 enters, and since the minimum ratio test is given by the second row, row 2, and since x4 is the basic variable in row 2 right now, so x4 will be the leaving variable, so which means that I'm going to actually pivot on this entry now. Okay, so as a result, we have x2 enters, and x4 leaves the basis. Any questions so far? So it's a very simple algorithm, right? Very simple idea, basically. All right, so what do I do next? Well, this is crucial. This is important. So essentially what I'm going to do is I'm going to keep x3 as a basic variable, okay? But I'm going to replace the old basic variable x4 with the new basic variable x2, okay? So I'm going to swap basically x2 and x4, so which means that x2 now will assume the role of x4, okay? In the new tableau, x2 will assume the role of x4 in this tableau. So essentially, which means that the column underneath x2, I'm going to make it look like the column underneath x4. Okay? So that's essentially the same as saying that I'm going to pivot on that entry, and then I'm going to try to zero out everything else in that column. And let's try to do that. So what's the first step? First of all, I need to make that circled entry equal to 1, basically, right? So I'm going to divide row 2 by 1. And if I do that, I have 0 minus 1 over 2, 1, 0, 1 over 2, and the right-hand side value is 4. Okay? Now, what's the next step? For example, if I look at row 0, I'm going to multiply this row by minus 3 and add it to row 0, basically, right? And if I do that, then the entry underneath x2 in row 0 will be 0, right? So I want to zero out this entry. So which means that I'm going to multiply this new row by minus 3 and add it to row 0. And if I do that, this does not change. I have minus 1, minus 3 over 2, so that's plus 3 over 2. So I'm going to have 1 over 2, I guess, right? Then I'm going to multiply this by minus 3, and I have plus 3, so this becomes 0. So this does not change. This gives me minus 3 over 2 plus 0, so I get minus 3 over 2. So from here I have minus 12 plus 0, so I'm going to have minus 12, basically. Did everybody follow that? So, okay. All right, so what's the final step? I need to also make sure that this entry is equal to 0. Okay. And to do that, I can simply multiply this by minus 1 and add it to row 0. And if I do that, I have 0. I'm going to have plus 1 over 2, plus 1, so I have 3 over 2. I'm going to have minus 1 plus 1 is 0. So this entry does not change. I have minus 1 over 2 plus 0, which is minus 1 over 2. and I have minus 4 plus 6, and the right-hand side will be equal to 2, basically, right? And hopefully I didn't make a mistake. So it looks correct, okay? All right, so what are my basic variables now? So once again, I mean, it's very easy. So, z is always basic in row 0. We never count it, okay? So I'm going to look for the columns of the identity matrix, okay? So where is the second column of the identity matrix? x3. So x3 basically is the basic variable in row 1, okay? And the last column of the identity matrix appears right here underneath x2. So x2 becomes the basic variable corresponding to row 2, okay? And my basic variables are now x3 and x2. And their values are given by 2 and 4. And what are my non-basic variables? I have x1 and x4, and they're both equal to 0. And my objective function value, what's the new objective function value? So it's going to be minus 12, basically, right? So I'm going to read it from the right-hand side of C. So as a result, I have minus 12. Now let me go back to my picture again. Which corner point does this correspond to? So remember, this is another basic feasible solution, basically, right? Okay, it's a basic solution, it's feasible. So it corresponds to actually this point right here. So we started from the origin, and we moved up to this point, and the objective function improved from 0 to minus 12. Okay? So one thing that I'd like to draw your attention to is the following. So this was the basic variable that sort of wins the minimum ratio test, right? So, okay, that has the smallest ratio. And the smallest ratio was equal to 4. Okay? Now over here, the value of x2 is also equal to 4. Okay? So is that a coincidence? Well, if you think about this a little bit, it's no coincidence at all, because that tells me the largest value of x2, right? The largest value of x2 can take while still remaining in the feasible region, staying in the feasible region. And since I want to increase x2 as much as I can, obviously the new value of x2 should be the same as the largest value it can take, basically, okay? So as a result, indeed, the right-hand side of x2, or the new value of x2, will be equal to 4, because the 4 is the best I can do. Okay? Does that make sense? Yes?
What the largest value of x2 changed? Like it was 6 and now this time it changed to 2.
Okay, so why did it change?
I think because we changed the basic.
Well, because if you look at row 1, okay, so initially x2 was 0, so now I'm increasing x2, and x2 and x3 have the same sign, so if I increase x2, x3 should decrease as well. Okay? So as a result, the new value of x3 now decreases to 2, basically. It was 6 originally, now it's gone down to 2. Okay? All right, so now I'm going to ask myself the same question again. Is this the best I can do? No, so now my non-basic variables are x1 and x4. Okay, so what happens if I increase x1? Well, if I increase x1, z and x1 have the same signs, then z has to decrease, basically, right? Okay? So what am I going to do? Well, I want to decrease z, okay? So as a result, I want to increase the value of x1. If I want to increase the value of x4, then z actually has to increase, right? So as a result, increasing x4 is not a good idea. So as a result, x1 is the entering variable. So which means that essentially, to determine the entering variable, we're going to look for a non-basic variable with a positive coefficient in row 0. Okay? This time positive, right? So for a minimization problem, positive. For a maximization problem, we're going to look for a negative coefficient. That's the only difference, basically. Okay? All right, so now what's the leaving variable? Well, once again, we're going to do a minimum ratio test. Okay? I'm going to look at the column underneath x1 for row 1 and row 2. Okay? And from the first row, from row 1, I'm going to have 2 divided by 3 over 2. 2 divided by 3 over 2 will give me 4 over 3, basically, right? Now, what about row 2? Well, you have to be careful because this is something we discussed last time. So if there is an entry which is not positive here, then there's no ratio, basically, okay? Why is that? Because if I increase x1, then the value of x2 will also increase as well, because the coefficient here is negative. So if I want to satisfy this equation, this is the coefficient of x1, this is the coefficient of x2, and they have actually different signs. Okay? If I increase x1, then x2 will increase as well. Okay? So which means that increasing x1 will never make x2 negative, basically. Okay? So as a result, row 2 does not give you any restriction in terms. So you can increase x1 as much as you want, and you will never violate the second equation. Does that make sense? Okay? So which means that here there is no ratio, basically, which we indicate by a cross. Well, since there's only one eligible variable, that's going to be the leaving variable, basically, right? So since there's only one, of course, that's the minimum ratio. So as a result, x3 will be leaving. So x1 enters and x3 leaves. So which entry am I going to pivot on? Well, so I'm going to look at the column of the entering variable. I'm going to look at the row of the leaving variable. And the intersection will be the entry that I'm going to pivot on, okay? So now x1 will become the new basic variable and x3 will become the new non-basic variable, okay? So one thing that you should pay attention to is the following. Between that solution and this one, there's exactly one basic variable in common, right? So essentially x3 is a basic variable here and x3 is also a basic variable here. But x4 was basic here and x2 is basic here. So basically, in this case, m is equal to 2, okay? And we have m minus 1 variables in common, basic variables in common. So which means that we have one basic variable in common, which means that these two are adjacent basic feasible solutions, basically, okay? And indeed, if you look at the picture, these two are indeed adjacent to one another, right? Okay? All right, so let's do one more step then. All right, so what's my first step? Well, I need to make the circled entry equal to 1. Okay, so how am I going to do that? Well, I'm going to take this row and multiply it by 2 over 3, basically, right? So, or divide by 3 over 2, that's the same thing. Okay, if I multiply row 1 by 2 over 3, then I'm going to have 0, 1, 0, 2 over 3, and minus 1 over 3. And the right-hand side value will be 4 over 3. Well, once again, the right-hand side value is the same as the minimum ratio, basically, right? Okay, that's not surprising. Then I'm going to multiply the new row 1 by 1 over 2 and add it to old row 2. Okay? And if you do that, you have the following. So 0, 0, 1, 1 over 3, 1 over 3. And the right-hand side value is 14 over 3. Okay, and finally, I can take this row and add it to row 0. Okay, I'm sorry. I'm going to multiply this by minus 1 over 2 and add it to row 0. Okay, and if you do that, then you have the following. So you have 1, 0, 0, minus 1 over 3, minus 4 over 3, and right-hand side is minus 38 over 3. So once again, what I do is I take the new row 1, multiply it by minus 1 over 2, and add it to old row 0, basically, okay? All right, so now what are my basic variables? Well, what's the basic variable for row 1? So I'm going to look for the second column of the identity matrix. So it's right here, it's x1. And finally, for row 2, it's going to be x2. Okay? So my basic variables then are x1 and x2. And their values are 4 over 3 and 14 over 3. And my non-basic variables are x3 and x4, and both of their values are 0. And what's my z value, the objective function value? Minus 38 over 3, okay. Is it better than minus 12? Yes, actually. So this is better than minus 36 over 3, basically, right? So we improved the objective function. We made it smaller. Is this the best we can do? Well, so if I look at my non-basic variables, if I increase x3, then z has to increase, basically, right? The value of z has to increase. And similarly, if I increase x4, then z has to increase as well. So indeed, this is the best I can do, okay? So basically, this is my optimal solution. And over here is my optimal value. Let me go back to my picture again. So what's the corresponding corner point here? Well, there's no surprise. It's essentially this point right here, okay? So the simplex method starts with this solution, first move to this corner point, and from this corner point, it moves along the edge, along this edge, and it finds the optimal solution in 2 steps, okay? Now, one thing you should pay attention to is the following. So, for example, the simplex method never actually looked at this corner point, right? Okay? So if we compare this with our simple-minded algorithm, so the simplex method realizes that there's no point in looking at this corner point right here, okay? So this is why we say that the simplex method actually looks at corner points in a systematic way, in a smart way, okay? So it does not blindly look at all the corner points. It just looks at the sort of relevant or interesting corner points, so to speak, okay? So here in this example, there are 4 corner points, but simplex is not even looking at this corner point right here. And what's the reason for that? Because, well, if you move from this corner point to this one, you would actually make the objective function value worse. Okay, so as a result, this solution can never be optimal. Okay. Just a quick question. So, does everybody understand why we don't apply the minimum ratio test here? Okay. Any questions? Yes. That's a good question. I'm going to do examples about it later on, okay? The quick answer is that, so if you have, more than one variable that can enter, okay, in principle you can pick any one of them, okay? But later on we're going to see that sometimes you have to be careful, okay? So when we talk about some other issues, in theory, as I said, it doesn't matter which one you pick, but in practice it might, okay? So we're going to talk about that later on. Other questions? All right, so let me give you one more example then. Example number 3. And this is an example that has alternate optimal solutions. So let's consider the following example. I want to maximize 2x1 plus 4x2, subject to x1 plus 2x2 is less than or equal to 5, and x1 plus x2 is less than or equal to 4. And both variables are non-negative. So this is again a problem with only 2 variables, which means that I can solve it graphically. So let me start with the first constraint. What does the first constraint look like? Well, if x1 is 0, x2 is 2.5, basically, right? And if x2 is 0, x1 is equal to 5. So it actually goes through these 2 points. So this is 2.5 and this is 5. And which is the correct side? Which side should I pick? So 0, 0 is feasible, so as a result this is the correct side. Okay. What about the second constraint? Well, it goes through 4 and 4. So 4 here and 4 here. So as a result it actually looks like this constraint right here. Okay. So that's the line corresponding to x1 plus x2 equals 4. And since the origin is feasible, again, I'm going to pick this side of the line. Then I have non-negative 2 of x1 and x2. So my feasible region will be given by the intersection of those 4 half spaces, which is that area over there, okay? All right, so what's next step? So this is a maximization problem. I'm going to draw the, which line? Isopropyl line, exactly. And And so let me look at the equation 2x1 plus 4x2 equals 0. So it goes through 0, 0. Okay. And I'm going to need one more point again. So if x1 is 2, for instance, x2 will be minus 1, right? So if x1 is 2, x2 is minus 1. So minus 1 is somewhere over here. So it will actually go through these 2 points. So that's my isoprofit line. What's my c vector? So it's given by 2 and 4. And if you draw it properly, you're going to see that it's perpendicular and points in this direction. Now, one thing you should pay attention to is the following. So if you look at the ratios of coefficients of 2 to 4, which is equal to 1 over 2, that's same as the same ratio here, right? Okay. So which means that the isoprofit line and this line are actually parallel to one another, right? They have the same slope. So which means that the best I can do is actually just, push this as far as until it coincides with this constraint. So which means that everything here is optimal. So we have alternate optimal solutions, right? So now the question is the following. So how does the simplex method actually behave in this case? Okay, so so we know that the simplex method only works with corner points. So the question is, how can it sort of realize that there are multiple optimal solutions? Okay, so that's exactly what we're going to do now. All right, so once again, let me quickly set up the tableau. So I have z, x1, x2. I'm going to add again slack variables x3 and x4. So what does rho 0 look like? Well, it's minus 2, right? So, you said z equals 2x1 plus 4x2. Then you put everything on the other side. So you have minus 2, minus 4. Please be careful about that. 0, 0. Right-hand side is 0. So what does the first constraint look like? 0, 1, 2. 1, 0, 5. And then over here I have 0, 1, 1. 0, 1. And the right-hand side value is 4. Okay, so what are my basic variables? Well, I have z here. I have the second column of identity matrix here, so I have x3 for row 1, and I have x4 for row 2. I'm going to have x3 and x4, and their values are 5 and 4. My non-basic variables are x1 and x2. They're both equal to 0. And the objective function value currently is equal to 0, right? So once again, this corresponds to the origin. Okay, since x1 and x2 are 0, that's the solution we have. Now, this is a maximization problem. Okay. So is this the best we can do? No, so which variable should I increase? Well, this brings us back to your question, basically. Okay, so in this case, I may either increase x1 or x2. Okay. So, one thing you should sort of pay attention to here is the following. So, if you look at row 0, so z and x1 actually have opposite signs, okay? And z and x2 also have opposite signs, okay? On the other hand, so which means that, if I increase x1, then z will increase. If I increase x2, z will also increase, basically, right? So, so I have a choice here. But the problem is that, so if you look at row 0 once again, if you increase x1 by 1 unit, then z increases by 2 units, right? Okay. On the other hand, if you increase x2 by 1 unit, then z increases by 4 units. Okay. So intuitively, it makes sense to try to increase x2, right? Because that gives you a larger increase in the objective function value. Okay. So that's exactly what we're going to do. So I'm going to try to enter x2. Okay. And what's my leaving variable? So I'm going to do a minimum ratio test. Okay, I'm going to look at the column underneath x2, except for row 0. Both of them are positive. So they will both enter the minimum ratio test. So what's the ratio for row 1? So you can always divide the right-hand side by the entry underneath the entering variable. So you have 5 over 2, which is 2.5. And then for the second one, you have 4 divided by 1, which is equal to 4. So what's the minimum ratio? Obviously, it's the first one. So which means that x3 leaves, exactly. And what am I going to pivot on? So I'm going to pivot on this entry, basically, right? Okay. So let's just do that quickly. So, well, let me also say that x2 enters and x3 leaves. So just like we did in the previous example, now we want to actually, from here, we want to increase the value of x2, so we want to move in this direction, basically, okay? All right, so I need to pivot on that entry. Okay, what's the first step? Divide row 1 by 2. So remember we number rows as row 0, row 1, row 2. So I'm going to divide row 1 by 2. And if I do that, I have 0, 1 over 2, 1, 1 over 2, 0, and 5 over 2. Once again, note that the right-hand side is the same as the minimum ratio test. Okay, value of the minimum ratio test. Then I'm going to take this row 1, multiply it by, let's say, minus 1, and add it to row 2. Right? So to make the entry here equal to 0, I'm going to take the new row 1, multiply it by minus 1, and add it to row 2. And if you do that, you end up with the following. So 0, 1 over 2, 0, minus 1 over 2, 1 and 3 over 2. So that takes care of row 2. I also need to take care of row 1, row 0, rather. So which means that I'm going to take the new row 1, multiply it by 4, and add it to row 0, basically, right? So now I want to make this entry equal to 0. Okay? And if you do that, you end up with 1, 0, 0, 2, 0, and the right-hand side value is equal to 10. Okay? So now what are my basic variables? Well, I have z here. What's the basic variable for row 1? x2, exactly. And for row 2, it's going to be x4, right? So my basic variables are x2 and x4. And their values are 5 over 2 and 3 over 2. And my non-basic variables are x1 and x3. And both of them are equal to 0. And my objective function value is equal to 10. Let me come back to this picture. So what's the corresponding solution, corresponding corner point? Well, x1 is 0, x2 is equal to 5 over 2, so which is exactly this point right here, okay? And from the picture, we know that that's an optimal solution, okay? So what does the tableau actually tell us? Well, this is a maximization problem, and if I look at row 0, there are no non-basic variables with a negative coefficient, okay? So which means that this is already optimal, basically, okay? Well, so the question now is, we know that there's another optimal solution, another corner point optimal solution, which is this one, okay? So now the question is, how can we find that optimal solution using this tableau? Now here's a crucial observation. So just look at your non-basic variables. So your non-basic variables are x1 and x3, basically, right? Okay. So now if you increase x3, okay, since there's a positive coefficient here, then the value of z will decrease, basically, right? Okay, so you don't want to do that. On the other hand, if you look at x1, the coefficient of x1 is equal to 0. Okay, so what does that mean? Well, if I increase the value of x1, how does z affected by that? How is z affected by that? Exactly. So as a result, I mean, from this tableau, since x1 is a non-basic variable, and since its coefficient is in row 0 is equal to 0, that means that if I increase the value of x1, then the value of z will not change. Okay? So as a result, what I'm going to do is the following. Let me try to see what happens if I try to increase x1. Okay? I know that my z will not change, but will I get a different solution? Okay, that's exactly what I'm going to do. So now I'm going to enter x1. Okay? So if x1 enters, then I need to determine the leaving variable. So for that, I need the minimum ratio test. What's the ratio for row 1? So I'm going to have 5 over 2 divided by 1 over 2. so it's equal to 5. What about row 2? I have 3 over 2 divided by 1 over 2. And that ratio is equal to 3. And obviously 3 is the smallest ratio. So as a result, the second row wins the minimum ratio test. Okay? So what's the leaving variable?
Why didn't we choose x4? It also doesn't make change when we increase it.
Well, x4 is already basic. Okay? We're looking at non-basic variables. Okay? We cannot change basic variables. We can only increase non-basic variables from 0. Okay? So x1 enters and x4 leaves. Okay? So which means that I'm going to now pivot on this entry right here. And let's see what we have. So if I do that, again, I'm going to start with row 2. I'm going to pivot on that entry. Okay? So I need to make the circled entry equal to 1. So which means that I need to multiply row 2 by 2, basically. Okay? And if I do that, I have 0, 1, 0, minus 1, 2, and the right-hand side is, sorry, minus 1, 1, and the right-hand side is 3. Minus 1, 2, sorry. Right-hand side is 3. I'm just multiplying everything by 2, right? So if I do that, that's exactly what I have. Then I'm going to multiply this by minus 1 over 2 and add it to row 1. And if you do that, you have 0, 0, 1, 1, minus 1. And the right-hand side value is 1. And then finally, well, there's nothing I need to do about row 0, because row 0 already has a 0 here. So I'm just going to copy row 0. So 1, 0, 0, 2, 0, and the right-hand side is 10. Okay? So again, z is the corresponding variable in row 0. What's the corresponding variable in row 1? So it's going to be x2, right? So it's the second column of the identity matrix. I have x2. What about row 2? So it's going to be x1. Okay, so what are my basic variables then? Well, they're given by x2 and x1. And their values are 1 and 3. And my non-basic variables are x3 and x4. Both of them are equal to 0. And the value of c does not change, so it's still equal to 10. Well, is this a different solution? Actually, it is, right? Because the value of x1 and x2 changed. So x1 is equal to 3, and x2 is equal to 1. And that's exactly this corner point right here, basically. Okay? Now, is that also an optimal solution? Yes, it is. So this is also optimal because there are no negative entries in row 0. Well, so what did we find? Well, we found two different basic feasible solutions which are optimal at the same time, right? Okay? So once again, if you look at row 0, there are no negative coefficients. So as a result, this is already the optimal solution. Now, by the same reasoning, if you look at your non-basic variables, we have x3 and x4. If I increase x3, then z will decrease. Okay, so I don't want to do that. If I increase x4, then the value of c will not change, basically, right? By the same reasoning. So what happens if I enter x4 again into the basis? Well, I actually get exactly this again, okay? So if I try to increase the value of x4, then x1 wins the ratio test because that's the only eligible variable. Then you're going to pivot on this entry, and if you do that, you get exactly this tableau right here, okay? So what does this mean? So this means that if you find an optimal solution using the simplex method, and if there's a non-basic variable whose coefficient is 0 in row 0, then you can enter that variable and you can obtain a different basic feasible solution with the same optimal value. Okay? So this is exactly how simplex method actually detects if there are alternate optimal solutions. Okay? So just like I said, so for example in this case x4 is a non-basic variable whose coefficient is 0. So if I increase x4, then x1 will leave and we get exactly the previous solution again. Okay? So essentially both basic feasible solutions are optimal. And what if I'm interested in computing a solution such as this one, for instance, okay, which is not a corner point? So how can I do that using these solutions? Well, so we can look at the line segment that joins them, right? And if you look at your notes, we have a formula for that. That includes lambda. And so is the following solution. So if I simply look at my x1, x2, x3, and x4, I can write this as 1 minus lambda times my first solution, which is given by 0. x2 is equal to 5 over 2. x3 is equal to 0. And x4 is equal to 3 over 2. So that's my first point. Okay. And then I'm going to multiply by lambda times the second solution. Okay. The value of x1 is equal to 3. The value of x2 is equal to 1. And x3 and x4 are equal to 0. Okay? And then if you just compute that, you get the following. So you get 0 plus 3 lambda. You get 5 over 2 minus 5 over 2 lambda plus lambda is 5 over 2 minus 3 over 2 lambda. Thank you. Then you have 0 for the third variable, and the fourth variable becomes 3 over 2 times minus 1 over lambda. 1 minus lambda, sorry. So both basic feasible solutions are optimal, and if you recall, if lambda is between 0 and 1, this gives you all solutions between these two solutions, basically, okay? So for all lambda between 0 and 1. And if I just look at the x1 and x2 components, basically, as lambda changes, I'm actually moving on this line segment, okay? So when lambda is equal to 0, I obtain this solution. And when lambda is equal to 1, I obtain this solution. And as lambda changes, I get all the solutions in between, okay? So as a result, if there are alternate optimal solutions, then the simplex method will tell you that there are alternate optimal solutions, and it can find all of them, basically, okay? Questions? Yes? So that's a good question. So the question is, is this a good algorithm, basically, if you have, let's say, 100,000 variables or something like that? So that's a good question. So let me tell you that. So right now, all the solvers that you're using for your project, Excel solver, Express, and so on and so forth, they all use this algorithm, basically, okay? So essentially, there are ways to sort of speed up this algorithm. Okay, so I'm not going to talk about that in this class, but you can make this algorithm work faster. Okay, and the second thing is that if you compare this with the simple mind algorithm that we had, that we mentioned like earlier, this algorithm does not necessarily look at all corner points. So that's the important property of that. Okay, so once again, for example, this algorithm never looks at this corner point. Okay, so which means that you can have millions of corner points for your LP problem, but the simplex method may look at a very small subset of them. Okay, so that's the reason why this algorithm actually works well. Okay, so it does not compute all corner points; it only looks at relevant corner points, so to speak. Okay, so as a result, in practice, this is a really good algorithm, basically. Okay, other questions? All right, good luck with your exams. See you next week.